Hello everyone, in this video I'm going to explain the problem E, decryption of the code forces round 671 div 2. The problem is that we are given a composite number n and which we have to put all the divisors of n greater than 1 in a circle, and we can choose the order of the numbers in the circle by ourselves. And then what in one move what we can do is we can choose two adjacent numbers and insert their LCM between them, and we can do as many as moves such kind of moves as we need it. And a message is called decrypted if the adjacent numbers, every two adjacent numbers, are not coprime. And this kind of situation, the configuration is always possible. So we have to find the minimum number of moves, this kind of moves that we have to do to decrypt the message and show that the initial, and we have also have to show that what order we will choose initially of the dividers in the circle. So let us try to understand this problem in the whiteboard. So let us say we have given this number n, and it has say k dividers. So we will put all the k divisor in the circle. Like this is the first divisor, this is the second divisor, and this is say third divisor, and all the way to the last divisor, which is a ks divisor. So the situation is good, and the situation that we want to achieve will be the situation in which any two adjacent elements, let us say this first and second, or second or third, have the GCD between them to be greater than 1. If the GCD between them is not greater than 1 and it is actually equal to 1, let us say it is equal to 1 for the fourth and the fifth divisor, then we will put a number which is LCM of this fourth and fifth divisor, so that now the GCD between this and this and this will be greater than 1, and we have the situation to be resolved in this part of the circle, and we have to resolve the situation in the complete circle in the minimum number of moves. So now let us try to understand this problem in a more general way. So let us say we have given this number, composite number n. So n, sorry for the poor drawing. So yeah, we are given this number n. So let us say the prime factorization of this number n to be p1 raised to power e1, its exponent to be e1, and then let us say the second prime number to be p2 raised to power e2. Actually these numbers are multiplying each other, so n is equal to p1 raised to power e1, p2 raised to power e2, all the way to pk raised to power ek. So let us say this is the prime factorization of n. Now what we can do, we can arrange the numbers first. First all the numbers we can arrange in the circle which has at least p1 in the divisors, so that is we can put all the numbers of the such form initially in the circle with the exponent of p1 to be greater than equal to 1, whereas all the other numbers from p2 to pk, their exponents can be greater than equal to 0. So we will put such kind of numbers initially, and after that we will put the numbers of the second kind in which there will be at least p2 in the divisor. So the exponent of p2 will be greater than equal to 1, whereas the exponent of p1 will be 0 for sure, because we have taken all the configurations of p1 already up to pk, whereas the exponents of p3 to pk can be greater than equal to 0. Not exactly they should be greater than 1, equal to 1, but they can be also equal to 0. So the last number will be the number of the kind in which the exponents of pk will be greater than equal to 1. So let us, for the sake of simplicity, assume that we will put here the number between the first and the last to be exactly a number which is having p1 and pk, the exponents of p1 and pk to be 1 and 1. So we'll put p1 into pk here in the between the first and the last kind of numbers. And now between all other kind of numbers, let us say between this first kind of numbers and the second kind of numbers, we will put the neighbor from the first kind in such a way that it has at least p2 exponent to be 1, and when it and the number which we will put in the boundary from p2 to p3 kind of numbers will have at least P2 and P3 both in their exponents, so that there is no dispute between here and here, right? So how we will achieve this using, and we will going to achieve this, we will going to see this in a minute. But before that, let us try to understand what case, like in this case, how we will not have to perform any move, and in what case we have to perform a move for sure. If we have only one prime vector p1 with any exponent, then there is no dispute, because we can put p1, p2, p1, p1 square, p1 3 up to p1 e1 in the circle without any problem, because any exponent, any two adjacent elements will have definitely p1 as their GCD. So there is no problem if we have only one prime number p1, one prime number p1 with any exponent. Let us say we have two prime numbers p1 and p2, right? So now what we can do is, if the exponent is equal to 1, both the exponent is equal to 1, then even if we put p1 into p2 in between both of them, but we'll still have a problem. We'll still have a problem because they have two neighbors. Like in this neighbor where p1 and p2 are adjacent to each other, there is a problem because the GCD is 1. So this configuration will definitely need one move in which we have to put p1 into p2 here, so that we can resolve the dispute. But other than that, let us say if p1 and p2 we have two primes where one exponent of 1 is greater than equal to 1, greater than equal to 2, and the other exponent can be even 1. In that case, we will still don't have any dispute, because we can put with p2 at one neighbor, we can put a number like p1 into p2, p1 raised to power 1 into p2, and then we will have the number of divisors where p1 will definitely be there, and in the very end we will put a divisor. Let us say we can put any power of p1 which can go up, like if p1 has power up to ek e1, so we can put p1 e1, and then we can put p2 here, so then there is no dispute here, and also there is no dispute here, right? So there is no dispute if we have two prime numbers where the exponent of 1 is greater than equal to 2 and exponent of 1 is also greater than equal to 1, right? And if we have three prime numbers, then there is no problem at all, because what we can do is, like we here in p1 we have this number p1, right? And then we will have p2, and then we will have p3. We can put the numbers like this. We can put here p1 into p3, and then all the numbers of the form in which the divisor is, in which p3 should definitely be there, will come here, and then all the numbers which have p2 as their divisor will be there, and between and p2 the numbers which have p1 in their divisor will definitely be there. So then there will be no dispute, because in the border we will have elements from p1 which have at least p2 in their exponent, and in the border from p2 to p3 we will definitely have an exponent here where p2 also and p3 should also be there, and here we will have an element where the exponent of p3 and p1 should at least be 1, at least one element is definitely there. So we have understood from there this whole examples, that if we have only two prime numbers and their exponents are 1, then we have to make one move. Otherwise we don't have to make the move, but we have to adjust the divisors of all the numbers in a proper way. So now I told you, corresponding to p1 we will have numbers of such kind in which there is p1 will definitely be there, right? P1 exponent will definitely be greater than equal to 1, whereas other exponent like p2 all the way to pk, their exponents can also be greater like 0, doesn't matter, but their exponent will also go from 0 to their final limits, right? So corresponding to p1 we will have numbers, such kind of numbers, and this we will push that this kind of numbers in a vector corresponding to p1 corresponding to index 0, because the vector will start from index 0. Corresponding to index 1 we will push all the numbers in which p2 will definitely be there, right? Whereas p1 will not be there, because p1 is already covered. And the other numbers from p3 to pk, they will have an exponent to be greater than equal to 0 all the way to their limits, to their limit exponents, right? And then corresponding to index k minus 1, we will have this prime number pk with the numbers in this vector will be of the following form, in which the exponent of pk will be greater than equal to 1. Like if pk has exponent say up to ek, so the numbers of number in this vector corresponding to this prime number pk will be p1 will be pk raised to power 1, pk raised to power 2, pk raised to power ek, up like this kind of numbers will be there, right? So we will gonna do this, and then first of all we'll achieve this vector, right? And also let we have since we have told ourselves already that corresponding to the first prime number and the last prime number k prime number, we will gonna have in the k prime number this in this vector k, we will have already one number we will already push initially, and which will be p1 into pk, so that there is no dispute between the first and the last element. And that's why we will push in this array already one element. We will push initially we will push this element p1 into pk, whereas when we will push in p1 we will not push this element p1 into pk, because p1 has exponent greater than equal to 1 and other exponent are greater than equal to 0. This condition is holding, but we'll still not push in the p1, we will push it in the pk, and we will also push in the position where p1 and pk are intersecting, so that there is no dispute, right? So let us now see the code to understand this a little bit better. So here we have input, we are inputting this number n, we are keeping a number of a vector for the prime and their exponents. So we are starting with the index 2, and if the index is dividing the number n, we will push that in the index in the prime, and we will also push the index the exponent to be 0 initially, and as much as the index is dividing the number n, we will gonna increase the exponent. And then if let us say we are dropping the value of n, and it's still greater than 1, then it means that n is also that the remaining number that which is left is a prime, so we'll push that prime and its exponent in because its exponent will be 1 in the prime and exponent array. And then let us see the size of the x prime factors to be k, that we have k prime factors with k exponents, and we have a vector of int which is dk, which I told you already that corresponding to p1 we will have d0, which will store all the numbers of such kind in which p1 will definitely be there, except this number p1 into pk, whereas in d1 we will store all the numbers in which p2 will definitely be there, and in the pk we will store all the numbers in which pk will definitely be there, and also this p1 and pk number will also be there. So we will push that already in the final dk minus 1 p1 into pk, right? P0 indicates p1 in our explanation, right? So in the DFS traversal, what we are doing, we will pass these three parameters, and what these three parameters indicates, let me explain you now. We have int current, and int x and int mp. Int mp denotes the index of the d vector, like it will go from 0 to k minus 1, and x will denote the element which we have to push in the d vector, and then this current will denote that how much factors we have considered till now. If we have considered all the k factors, then we can push from that point onwards, because we can only push when we have considered all the k factors, no matter what their exponents are. But when we have considered all the factors, then we can push even if they are having 0 initially, but then that will be the base case. Then we'll start multiplying this with p1 and their exponents, and like all the, it will be sure for sure that for any prime number, their exponent will go from 1 to the final limit, which will be here in the case of p2 will be e2, in the case of p3 it will go from 1 to e3, in the pk it will be 1 to ek, right? So like I will explain here furthermore that in this DFS traversal, what we are doing is like, what will be the base case will be when we have considered all the k factors, like from p1 to pk. Then if our, like initially we pass this index to be -1, so if this index is -1, we not have to push anything, because the vector will always start from 0, right? And otherwise, if our factors are greater than equal to 2 and we have reached this k number of factors, Then if the number which we have to push is the first number and the last number which we have already pushed in the final dk minus 1, then we will also return. We will not do anything. Otherwise we will push in the corresponding index mp, we will push the number x, and then we will return, right? And because we are doing the DFS traversal, this current will go from 0 to k minus 1, so that this value will become 1 to k, and correspond to this it will go all the way from 0 to k minus 1 to reach here, because this is depth first traversal, like it will go to the depth. So first of all it will fill correspond to k minus 1 all the factors of pk, and then it will fill after filling all the factor of pk, then what it will gonna do, it will gonna do the like the recursion will broke out, and then correspond to the earlier current value which is k minus 2, then it will multiply this k minus 2 prime numbers factors, and then it will going to increase, and then will multiply with the pk minus 1. That is, like I can explain here like this. The DFS traversal, what is doing, the current one will go from 0 to k minus 1, because the depth will go all the way to the depth. So when the current will be k minus 1, then the current plus 1 will be k, right? Like when then this current plus 1 will be k, and since this will be k, then and the recursion is already break out here, because mp was initially minus 1, and it will be also minus 1 when we have reached all the depth. Then what we're going to do, correspond to this current, like correspond to this pk minus 1, we will want to multiply this all the way to the ek, from 1 to ek. We will multiply we will consider all the factors of pk minus 1. That is, I had told you already that we will consider all the factors pk greater than equal to 1, and after that the recursion will broke out, and then we will reach this pk minus 1. Like after we reach the depth, now we'll go from the depth to the top again. This is the df traversal. And then in the pk minus 1, what we will going to do, we will going to multiply the exponents of pk minus 1 from 1 to all the exponents of which we can reach, that is ek minus 1, like in here. And after that we will gonna increase this current value, and then when we increase the current value, then what we are doing essentially is we were gonna take the factor of pk also, which will be greater than equal to 0, right? So we will now then fill the vector pk minus 1 all the way here. We will go all the way to the p1 when we fill all the p1 like the d0 vector, right? Like this vector, when we have filled this d0 vector, this vector. So after that, after doing this filling of all those d vectors, what we are going to do, we have to select the boundary element, right? And then we have to also print answer as well. So answer will be 1 only when we have only 2 number of divisors, and their exponents are also equal to 1 and 1. Otherwise, if that is not the case, the answer will be 0, right? And what the configuration, the initial order that we have to print will be like that. What we have to do is, like correspond to all this decay vectors, we have to select the boundary element, right? But the boundary element of the first and the last vector is already selected, which is p1 into pk. So but the boundary element of these elements like I told you here, like I have just here, but like for example, when we have this divisor, all the elements of the kind p1, so when we will reach p2, then here in the p1 we will in all the divisor of p1 we will choose a one divisor which is also having p2 exponent to be equal to 1 or greater than equal to 1, right? So that there is no dispute here as well. So whenever we find any element in this divisor array which is also dividing by p2, we will gonna put that divisor in the very end of this p1. So here we are doing the same. Whenever we find that any divisor of the p1 is divisible by p2, we will want to put that divisor in the final as a final element of the divisor p1, and after that we will want to just print the order in which we have found in which p1 is there right now, and similarly from p2 to pk minus 1, and it will also be printed like the same order. And I have told you already that the final element, this element denote that the dk minus 1 is already carrying this p1 and 2 pk, so that will also be the final print, and it will be the final element that will be printed. So corresponding to this 30, what we have, like I can explain this with the help of example here with the 30. Corresponding to 30, we have this number of a divisor of 30 to be 2 to the power 1 into 3 to the power 1 into 5 to the power 1, right? So now, first of all, we will fill the divisor array of corresponding to this 2, but we will not push, and we will also fill the divisor array of 3, and we will also fill the divisor array of 5, right? We have initially using the code, what in the code what we are doing is like we are filling the final element of this 5, the whatever is the final element, we are pushing that this 2 into 5, that is p1 into pk, we are pushing that in the final vector. And after that, all the other divisor of which has 2 as its prime vector will be pushed in this correspond to this 2, that is 2 into 6 and 30, right? And there will be no other. And in correspond to 3, we will push this 3, and then we'll also push 15. And correspond to this 5, 10 is already there, we will also push then 5, and that's it. And now how we'll arrange this in the circle, like according to the code, like we have put this 2. As soon as we find that this now this the divisor 2 is not divisible by the next prime number, which is 3, so we'll not do anything. And when we see 6 is also divisible by 3, so we'll push 6 to the final, and then we'll just print 2, 30 and 6. We can also break from there and push, and then when we reach 3, there is no problem here because this 6 and 3, the GCD is 3, so there is no problem. And after that we will put 15. As soon as we find that 15 is also divisible by 5, so we will push in 15 in the line last. It is already last here, so no problem. Then we'll have this 5 and 10, but now this 10 we can also but we have reserved this 10 for this 2. When we find this 10 is also divisible by 2, so we'll push that 10 to the last, and then 5 and 10 will be printed like this. And since we have not to make any move, so the answer will be 2, 36, 3, 15, 5, 10 and 0. So this is the answer as well of this problem. I have taken some time to make you understand this problem. I hope you understand some part of it. I have not explained the problem D of this contest. D has been explained by many guys in the YouTube. Also, my recording was going quite poor. Like I was recording this E from 1.5 hour, and this like my battery was shut down. So anyway, let us terminate now.